This is section 13.7, part C. We have one example left, example 4 here. We're integrating the function y squared dA, which certainly doesn't raise any alarm bells yet. That should be easy to integrate. But let's take a look at the rather weird region we have to integrate over. I'm going to try and draw this. In the xy plane, we have x equals y squared, which is just a horizontal parabola. And then we have x equals 9 minus y squared. So that's a parabola shifted over with its vertex over here at 9. And then it opens the other way. It's been reflected across the y-axis. So that was x equals 9 minus y squared. X equals y squared minus 4. It's positive y squared, but it's been shifted to the left 4. So over here to about negative 4. Opens this way. And then x equals 16 minus y squared. So 16 is going to be out here somewhere. And then minus y squared, so it opens to the left. And what you can see here is that there are actually a number of different regions that are enclosed. I probably should have been more specific. So I'll tell you what. There's actually 4 different regions that are enclosed. I'm just going to pick one of them for us to work with. I didn't do that very well in the instructions. But let's do this one. Because of the symmetry, this one would be the same. If I wanted these, they would of course be different than the one we're picking, but they would be the same as each other. I'm just going to go with that one. So this is our region R. Now, I'm going to have something kind of similar to what I had before. The integrand isn't the problem. It's the region. If you can imagine, we would once again, if we tried to do, like, for example, vertical rectangles, we'd have a region over here, a different region in the middle, and another one on the right. So we're back to the situation of having 3 separate double integrals that we would have to do to integrate over that region. Let's see if we can use a substitution to fix that. Here, if I were to say, let's move the y squareds to the left hand. Yeah, let's go the other way around. Let's say that this one is y squared minus x equals 0. And here, if I brought the x over to the right-hand side, I would again have y squared minus x, but I'd have to bring the 4 over to the left, so that's going to equal 4. That would suggest that y squared minus x might make a good variable. So we're going to go ahead and let u equal y squared minus x. And then I have u equals 4 and u equals 0. Really nice, simple limits of integration for u. I'll do something very similar down here. And let's see here. I'm going to bring the y squareds over. So I would have y squared plus x equals 9. And here I'd have y squared plus x equals 16. So that's going to suggest to me that maybe letting v equal y squared plus x would be a good idea. And then I'm going from v equals 9 to v equals 16. Once again, that's going to make a very nice, simple region to integrate for our S. Let's sketch it right in here. U goes from 0 to 4. So there's my u-axis. Here's my v-axis, and it goes from 9 to 16. And here's our region S. All right, well that made that a lot nicer. Let's see what happened to our integral. The next thing we're going to need to do is to calculate the Jacobian. And in order to do that, we need to look again at our transformation equations. They were u equals y squared minus x, and v equals y squared plus x. Right now, if I were to add those equations together, it would certainly eliminate the x's, and I should be able to solve for y. So u plus v equals 2y squared. And let's see, I'd have a 1/2 u plus 1/2 v, but that would still be y squared. So the square root of that would equal y. I am going to take the positive square root, since in my region all the y's here are positive values. All right, if I go back to u equals y squared minus x, and I'm going to actually multiply this one by -1. So minus v equals minus y squared minus x. Now I'm eliminating the y's. So I have u minus v equals -2x. And if I divide by -2, I'd have -1/2 x plus 1/2 v equals x. All right, these are not quite as nice. This is a nice equation. This one not so much, but we'll deal with it. We do need the Jacobian, so let's get that next. All right, the derivative of x with respect to u, -1/2, and with respect to v, +1/2. The ugly derivative is going to be the y derivatives. So let's see here. The derivative of y with respect to u, I'll have a 1/2 times all of this to the -1/2. And then the chain rule, the derivative with respect to u on the inside is a times 1/2. That will be exactly the same for y sub v, since the chain rule on v is also a 1/2. So I'm going to put it over here as a 1/4 times 1/2 u plus 1/2 v to the -1/2. So let me spread this out a little more so I can see what's going on. That's really 1/4, and that negative exponent puts the radical on the bottom. All right, definitely need some more space here, so. My Jacobian is going to end up being, that'll become a -1/8 with that radical on the bottom. Subtract a 1/8, again with that radical on the bottom. And -1/8 and -1/8 is -2/8 or -1/4. So I think I'm going to leave that as my Jacobian. All right, we are ready to go ahead and set up our integral. Just a reminder from way back when, our integrand is y squared. And when I square the y, that's just going to become 1/2 u plus 1/2 v. So that's not too bad. I need to put in the absolute value of my Jacobian. There's my Jacobian. So absolute value of that goes in here. And then I'll go dv, du. The v's went from 9 to 6. Actually, you know what? Because the u's go from 0 to 4, maybe I'll do the u's first this time. Let's go horizontal, then I have the 0 to do myself. So I'm going to go du dv, where the u's go from 0 to 4, and the v's went from 9 to 16. All right. I'm going to do a couple of things here. First of all, obviously the absolute value will get rid of that negative, so I'm not too worried about that. And I'm going to pull the 4 in the denominator out, so I have a 1/4 out here. And then take a look at this. If you've got something divided by the square root of that thing, you're really just left with the square root, aren't you? It's like saying a over the square root of a is the square root of a. Or you could have written it as a times a to the negative 1/2 is a to the positive 1/2, which is the square root of a, right? All that means the same thing. So what I'm going to end up with here is actually just this 1/2 u plus 1/2 v to the positive 1/2 power. Think of it as the first power here minus the 1/2 power there. Du dv. Oops, I lost an integral. There we go. All right, again, not too bad. I do need a little substitution, just a regular substitution this time, so let me write that out. I'm going to let w be what's inside my parentheses. And I'm doing du first. So partial u of w with respect to u is 1/2, meaning 2 dw is equal to du. So this becomes w to the 1/2. And I'll replace the u with a 2 dw. I'm going to put the 2 out here and the dw in here. So on the outside I've got 2/4 or 1/2 now. And then the integral of w to the 1/2 would be w to the 3/2. Dividing by 3/2 is multiplying by 2/3, which I'll pull out. So I end up with 1/3 times the integral of, let's see, w was 1/2 u plus 1/2 v to the 3/2. And that went from u equals 0 to u equal 4. All right, we're getting there. For u equal 4, that would be 1/2 of 4 would be 2 plus 1/2 v to the 3/2. And then subtract, when u is 0, that would just be 1/2 v to the 3/2 dv. And when I put all in the calculator, including the multiplication by 1/3, didn't come out to anything very nice or recognizable. I got 18.79 for the value of that integral. All right, that brings us to the end of 13.7, and as a matter of fact, to the end of chapter 13.